Hi, everybody. We started a long time ago now. It's been quite a bit of time since we started, but just I want to share with you basically what I learned from one of your classmates, because I want to make sure that you also have the same understanding and you're on the same footage. So this is the work of one of your classmates, basically, and this is one of the worksheets so that you all are on the same page on the same thing. In the worksheet, you have 2 pages, and each page has 2 tables. You have tables A1 and A2, and you have tables, if you don't mind, you go down to the next tape, please. And you have tables B1 and B2, okay? Let's go up a little bit more. Tables A1 is formulas only. Table A2 is actually numbers. Let's go down now to the next page. Table B1 is only formulas. Table B2 is only numbers. How do we get these formulas and how do we get these numbers? It's a good question. Let's go above. Let's go back to the first page. We look at the process that we're talking about. This process is a cycle. This cycle is a 3-process cycle. Okay, this is the lab that we're talking about. This is a 3-process cycle. It doesn't matter where you start from. Let's start from any given point. We're starting in here from the lower arrow. If you don't mind, can you, okay, yeah, that arrow takes us from Vmax down to Vmin, okay? This is at constant pressure Pmin. So we write the equations for this one. Before I write the equations, there is another thing that we need to write, and I'm going to talk about that. Then there is the next process, which takes us from Pmin to Pmax at constant volume Vmin, okay? And then we have a third process that takes us from Pmax down to Pmin, or Vmin down to Vmax if you want to, at constant temperature TH. So these are the 3 processes that constitute the cycle. Since it's a cycle, we don't care where we start from. Now, the equations we know. We have 3 points in here of interest to us. We wrote the first point at the top in here, and the top in here has a pressure Pmax and has a volume Vmin, and has a temperature TH. So we wrote the ideal gas law in there, which says Pmax times Vmin is equal to nRTH. At this point, there is nothing suspicious about this equation or anything irrelevant about it. Everything is really lame at this point. We're going to talk about the relevance of every single term down the road. So this point that we wrote is the point on the top. And that point has a specific pressure Pmax and a specific volume Vmin and a specific temperature TH. We're assuming the number of moles is little n. We wrote also the second equation for the second point that has a Vmin in Pmin, and that is the point below immediately on that one. So it's immediately on the same line, okay? So the volume is Vmin, the pressure is Pmin, the product of these 2 is N, which is the same number of moles because we're assuming it's the same gas, it did not change, times R times Tc, because the temperature here, they're telling us it's Tc, it's a different temperature. The last equation is the last point that we're interested in, is where the pressure is Pmin, but the volume is Vmax. The number of moles is still the same, and the temperature has changed now to TH. So those are the 3 equations of interest to us. Also, now we need to talk about the processes. We wrote the first process at constant pressure Pmin. This process takes us from a volume Vmax down to a volume Vmin. The temperature changes from TH down to a temperature Tc. This process is an isobaric process because the pressure doesn't change. In that case, the Q, the heat, is equal to Ncp, the molar specific heat at constant pressure, times the difference in temperature. We went from TH to Tc, so the temperature went down, so we have to write the final temperature, which is TH. We have to follow the arrow, basically, which says the final temperature is TH, and the initial temperature is, the final temperature is Tc, and the initial temperature is TH, so I have to write Tc minus TH in here, correct? So up to this point, we're just following the formulas. The work in this case, you have to be careful in here. The volume changed from Vmax down to Vmin. And it's just the integral of PdV, but the pressure doesn't change, so it comes out of the integral. We followed the convention of the book in this lab. So we're going to use the positive sign. So the pressure is a constant. It comes out of the integral, and the integral of dx from Vmax to Vmin is just Vmin minus Vmax. So just the difference in volumes. So this is the work. The delta U in here, by the way, you cannot write delta unless you write explicitly. That's fine. Du is fine. Is always equal to N, the number of mole times the molar specific heat, which is CV, times the difference in temperature. Again, the final temperature is Tc and the initial temperature is Th. So everything looks good now. The only thing is we don't know what CV is, we don't know what CP is, but that we will find out during the lab, okay? Vmin, which is the next process now, the other arrow. If you look at the other arrow that at constant volume Vmin, that is the arrow that takes us from the pressure Pmin up to the pressure Pmax, and the temperature changes from Tc up to 2H. So that is this process. The work is 0 in here because the volume does not change. So we're in good shape now. Now, the heat, which must be equal to delta U, because W is equal to 0 according to the first law. So it's just going to be N times CV. It's always NCV for the energy times the final temperature minus the initial temperature. The final temperature is Th, the initial temperature is Tc. And again, we need to find probably what N is and CV is. The final process that takes us from Pmax down to Pmin through this isothermal, through the arrow that is curved a little, that change the volume from Vmin to Vmax, okay? So the temperature doesn't change in that process, which means the energy doesn't change. So delta U is equal to 0 in this process, okay? So we're left with W equal to Q. Remember, we're using the convention of the book. If we're using the convention that I use in the lecture, delta U and Q will have W and Q will have different signs. But in here, we're just following that. And that we saw in lecture is equal to N, the number of moles, times R, which is a constant, times Th, which is the temperature where this whole thing is happening, times the logarithm, the natural log of the ratio of the final volume, which is Vmax, divided by the initial volume, which is Vmin. So we're in good shape. Now, we need to find some relationship between CV and CP. This section of the lab, you write as many equations as you need for solving your lab. We know CP over CV is equal to gamma. So if gamma is given, we should be able to find CP and CV. And sure enough, if we solve that equation, in addition to the equation that we found that CP is equal to CV plus R, we can find CV equal to R over gamma minus 1, and CP is equal to gamma times CV. So it's going to be gamma times R divided by gamma minus 1, if you want to. So everything now is in terms of everything. Now, let's go to section A1 now. The table A1, I should say. We need to solve the first 3 equations to find what we need to find, because Vmax is given, Th is given, all of this grade cells, they're given, Tc is given, Pmin is given, gamma is given. If gamma is given, then clearly CV is known. And if CV is known, CP is given, is known, basically. You can solve for these equations. But let's find Vmin. And let's find N. N, if I look at the third equation from the top and start counting down, the third equation has Pmin in it. And guess what? Pmin is given according to that table. Has Vmax in it, and Vmax is given from that equation. Has R in it, and R is known to be 8.314. Th also is given according to that table. So we should be able to solve for N, and sure enough, the solution is Pmin times Vmax divided by RTH. So we're in good shape. So let's look at the second equation from the top. The second equation now has Vmin in it, which we don't know. Has Pmin, which is given. Pmin is given. Has N, which we just solved for it. Has R, which is constant, and has Tc, which is given. So everything is given, or we just solved for it, namely N. So we should be able to find Vmin. So if we go to table A1, we should express Vmin now in terms of everything that we know. So Vmin now, we are going to find it. Immediately under that cell, there is another cell that's where we find the ratio of Vmax over Vmin. Since Vmax is given and Vmin we just found it, we can solve for rho. okay? We don't do anything for the cell next to it for tau, which is the ratio of TH over TC, because both of them are given, so it's really given. The cell underneath that, where the number of the actual particles of that gas is going to be n, which we just solved for it, little n times Avogadro's number, which is given. So it's going to be the same formula times Avogadro's number. Now, the last thing that we need to solve for in table A1 is going to be P max. P max, the way we solve it, we will go all the way to equation number 1 from the top, okay? Equation number 1 has a P max in it, which we don't know, but it has a V min, which we just solved for. It has an N, which we just solved for, and has an R, which is known, and has a TH, which is known. So we should be able to solve for P max, and table A1 is done. We're in good shape now for table A1 in terms of formulas. Table A2 now. Just look at table A1, except sub the values now, that's all. So you just found the formulas from table A1, and you have the Vmax is 1,000 cubic centimeter, TH 400K, TC is 300K, and Pmin is 0.1 joules per cubic centimeter, and gamma is 1.4. So basically we have to solve these equations, that's all, and plug in the numbers. So we're done with table A1 and table A2. Let's go now to the next page, please. And let's look at these processes where the pressure is not changing, the volume is not changing, and the TH is not changing in the first 3 rows of table B1, okay? And let's go above, back to that section for the formulas. In the section for formulas, Pmin, we need delta U. Delta U is NCV-TC minus TH. That's the first cell, okay? Well, I don't know what N is, but N I just found it from this equation. Remember from table A1? So we know what N is. CV is given in terms of what is known, R over gamma minus 1, times the final temperature minus the initial, times the final temperature, which is TC minus the initial temperature, which is TH. All of them are given at this point. So the only thing that is unknown in this delta U is N and CV. So if I sub the value of N from what I just found and sub the value of CV from this, the last row, the last line of this equation is 3, we can find delta U. Go back into table, please, the second page. So now the first cell in table B1 is known because of that. Let's go to delta Q now. It says delta Q. It should really be Q and W in the same time. Let's go up, back to that cell, please. So we have the same process. We're still talking about Pmin, where the pressure doesn't change. We're still talking about the first arrow on the bottom in here, okay? Going from Vmax down to Vmin. So Q is equal to N, which we just found it from table A1, by the way, times Cp. And Cp is gamma times Cv, and Cv is just R over gamma minus 1. So we can sub everything. Times the difference in temperatures, and those temperatures are given. So we're going to plug the value of Q in there. And the same thing, we're going to plug the value of W, where W is Pmin. Do I know what Pmin is? I just calculated it. Or it's given, I'm sorry, it's given. It's given from table A1. Pmin is given. Vmin is not given. Vmin is what I just calculated in table A1. Okay? So I'm going to take the value calculated from A1 and minus Vmax. And Vmax is given, by the way, and that's going to be W. So let's go down to table A2, please. Table B2. Table B2, yes, correct. Table B2, now we have everything in the first row. Let's go to the Vmin. Vmin, W is equal to 0. Let's go back to the equations, please, to top of the first page. Okay, we're talking about the second process now. W is 0. So we plug in 0 there. That's it. We're done with that. And then we're going to do the Q and the delta U, which must be the same. So whatever we do for one, it's the same for the other one. Same thing. N, we just calculated it from table A1. CV is equal to R over gamma minus 1 times the difference in temperatures, which is TH minus TC. And we're going to plug in those values. Go down, please. So the first 2 columns of the second row, the same value I put it for delta U. No, up for table B1. Okay, there. So that's Q, and the one immediately to the left of it, that is going to be my delta U. So we're in good shape now. Let's go to the last one of these 3. Go back to the equations, please. And that is when the temperature is fixed. Delta U is 0. So we're done with that. And the W and the Q are the same. And it's equal to N, which we just calculated it from formula A1, times R, which is constant, times TH, which is given, times the natural log of V max over V min. And that ratio is rho from table A1. We calculated that one. So we're going to put whatever we calculate in there, we're going to put it in this formula in terms of what we know. So now we have the ln of this known value. And we have R, which is constant, TH, which is given, and N, which we just calculated from this formula. Let's go down now to table B1, please. Table B1, first of all, delta U is 0. I'm talking about the third row, which is at constant temperature. At constant temperature, delta U is 0, and then the Q and delta and W are the same value. Whatever you find for one, you find for the other. And I just told you what the answers were. Now, if you look at the first column of table B1, the first column, you have delta U. Add these values, and it should be the formula that you find in there. Okay, it should be actually 0. Okay, so you're going to check that. Now for the W net, which is the network, you add the 3 values in here. One of them is 0 for the third column. The third column on that table, you have W, you have 0, and you have another number that you're going to find. That's going to be the W net, which is the second cell in there. Now the Qn, you're going to look at the second column and see which one is going to be positive and which one is going to be negative. If it's negative, it's Q out. And there is only one that is going to be negative, which is the first one. And then there will be 2 positives, and those are going to be the Qn. And you're going to put them in the Qn when you add them up, and you're going to have the Q out, the negative value in here. Okay. When you're all said and done with this one, now the last table, table B2. And the last table B2 now, you just plug in the numbers. Remember table A2, go back up, please, to table A2. Table A2 has all the values. Now you have a value for N, you have a value for rho, you have a value for V min, and you have a value for P max, and you even have a value in here that says 10 to the power 23 times another number in here, okay? So you have everything in this one's in here, and you're gonna sub those values now. Go back down, please. Because all of this table B1 actually are formulas using those knowns, and now just plug in those numbers in here and you're gonna find the values. And that you have one worksheet. I know it's long and tedious, but there is another one. Believe it or not, this is preparation for your exam. Okay, which takes me to the second point that we decided to meet on today, namely preparing for the exam. So what are the things that we need to do? Can you stop sharing, please, the screen? Let me share with you my screen in here. Thank you, Alexis. You guys need to thank her because she brought up this issue. So let me first of all change the view to a student view. And minimize everything. To talk about the exam, because this lab is critical for your preparation for the exam. So so let me share this screen in here. So this is where we are right now. So we're going to have this session recorded and posted in here for all of you guys who are not here. And there is actually a question that was mishandled probably in the lab. So the homework, so you guys can look at it. But this is the actual exam. The actual exam is going to be available on Tuesday next week. Okay. So initially it was planned this week, but I postponed it because of the fact that we had some delays in the past, especially for this lab. We didn't really have extensive discussion about it. Okay. If you see a process like the one that we described in here, this is an engine. Why? Because the work is going to be in the cycle is going to be in this direction. It's going to be actually a clockwise motion. When you are in clockwise motion through the cycle, all the processes pointing in the same direction and they're clockwise. This is an engine. If it is going in the opposite direction, it's going to be a heat pump, a refrigerator, for example, or an AC unit, pumping heat outside. Okay. This example that from the lab, and all the lab are actually engines. They are all in clockwise motion. If you see it backward, that is actually a heat pump, not an engine. Okay. Now, if it is going in the same time and then it loops around and comes back up, now you really have to find which one is dominating. So if it loops around, you see, is it mainly clockwise? In this case, it's an engine. Is it mainly a heat pump? Then in this case, is it mainly counterclockwise? Then in this case, it's a heat pump. Okay. Actually, you have to do the numbers and find W. If you follow the convention of the book, you're going to find W positive for a heat and for an engine. If it is negative, it's going to be a heat pump. If you follow the convention of the lecture, it's going to be the opposite sign. But you have to be mindful of the fact that W, either you plug in the negative sign in it, like we did in the lecture, okay? And you start calculating. If it is negative, then it's work done by the system to the environment, energy lost in the form of work to the environment. That's what the negative stands for, lost, okay? Then it's an engine because it's doing work, really net work at the end. If the work turned out to be positive, that means it's energy added to the system in the form of work. So somebody is doing work on that gas, okay, compressing it. So in this case, it's a heat pump. Okay. If you follow the convention of the book, which probably you can interpret it as this way, I'll do my best to interpret it because I'm not convinced with the convention. But you have to be mindful of the signs. Please pay attention to the signs. You have to stick only to one, not both. Okay. If you put the positive sign in front of PDV and integrate, okay, and sum, find the area, basically. That's what the integral is. Find the area, right? Area of triangle or rectangle, or whatever the shape is. In that case, in the lab, it was this weird shape in there, okay? And if it's positive, you're saying in here, it's doing work against the environment. So it's an engine. If it's negative, it's having work done on it. Okay, then it's in this case heat pump. So the key thing in here is forget about the negative sign or positive. Just look at the direction of the processes overall. Is it clockwise? It doesn't matter which sign you take. It's going to be an engine. If you follow the clock, it is an engine. If it is backward, not following the clock, opposite to the clock, counterclockwise, this is actually a heat pump, okay? Whatever values in there, you're going to append them so that they do. The trouble with it is sometimes there is a section, it goes like this, and then it crosses, and then it pops up. It's like a figure 8, for example. Let me try to draw it in here. Let me stop sharing that screen and draw what I'm talking about. And let me first of all pull the thing, and let me open a new page in here. Untitled is fine. Oh, I need to have a title. What is today? 21st. We're not in August anymore. September 21st. Okay, so let me share the screen to tell you exactly what I'm talking about so that there's no confusion about this business in here. Okay, so a process like this one is described earlier. This is clearly clockwise. This is how the clock goes. So this is an engine process that does the same thing, but it's actually, I mean, it's in the same paths, but different directions. This is counterclockwise. This is a heat pump. Okay. Here is where it gets a little bit tricky, and you have to really pay attention to the numbers or the conventions in here. Let's say, for example, this process starts in here, goes like this, and then closes on itself like this one, for example. I have to find this area, which is clearly in the clockwise direction. So this part in here is acting like an engine, but this part in here, where the process is going this way, it's actually acting as a heat pump. Is this area more than this area? If it is, then in this case, the net behavior is whatever is in here. So this is actually going to be an engine. But if I'm going to do it this way, for example, it's the same thing, but in here it's clearly this area is less than this area, and this is going against the clock. And this is going with the clock. So in this case, it's going to be a heat pump. Okay. I mean, I know these are theoretical sometimes. Most of these engines are theoretical anyway. 3-cycle engines are not realistic anyway. So, but this is basically the idea behind all of these things. So you really have to pay attention to this type of calculations. All of them will involve, this is area, the work in here is easy to find. Because just, if this is a triangle and it's given to me, it's 1/2 base times height. I'm assuming that this is the pressure, I mean, this is the volume, and this is what the pressure is. So these values are given on a PV diagram. So I have a volume in here, V1, I have a volume V2, and I have a volume V3, I have a pressure P1, pressure P2, and I have a pressure P3. So all of these things are given to me. So if I want to really find the area for this section, this is easy. 1/2 base times height. This area is actually 1/2 base times height, but except the base is this one, and the height is that one. So that's all. This is a triangle, right angle triangles. So I don't really need to remember any of the other formulas. Of course, if you ask me what the heat is, then in this case, I have to be really careful with the heat because of the fact that this is actually, for this one, for this particular example, this Q, I'm going to call it Q1, is NCP times the difference in temperature, this temperature and that temperature. Since the pressure in here is P2 and the volume is V2, so this point in here has a specific temperature that I need to find, okay? And the temperature satisfies the equation. This temperature is equal to this pressure, P2, times this volume, V2, divided by NR, because of PV equal to N2. So it's P2, V2 over NR. So that is this temperature in here. But this temperature in here is P1 times P2 divided by NR. So this is equation in here. I can find it. So I can find everything basically in this diagram in here. So I find the temperatures. So this is going to be this temperature here minus this temperature if I'm going in this direction. Okay. So it's this temperature here minus this temperature in here. Okay. And then I can find this process. This is actually Q is equal to NCV. This temperature minus this temperature. This process in here, I don't know how to do it, honestly. So what should I do now? Oh, it's easy. Delta U is equal to 0 for the entire cycle. And I know what the area, what the W is, what the W net is, which is this area, which is the 1/2 base times height. And I can also find what the Q net is. The Q net is just 0. If I add 2 gamma to there, you're going to give me 0. So if I use the convention of the lab, Q net is equal to W net. Or if I use the convention that we use in lecture, Q net is equal to negative W net, depending on what you guys feel about it. You are at a point where you really need to make decisions on which format you need to go with. It doesn't matter. You're going to find algebraically the same value, and that's what matters. Okay? So the sign is just telling you which convention you're using. Now, you find Q net and W net, but you already have found 2 Qs in here. So all you have to do is find the third Q, which is in such a way that you have to add it to the other 2 and get 0. That the overall Q. So you know what this Q plus what this Q is plus what this Q is, so equal to the total Q net. So when I said I really don't know, I'm saying in the process up to this point. So there is a way of finding it. There is a way of finding everything. Okay, and that's the way to find it. Find the Q net, and since you know the other 2 Qs, then you can find the Q that you don't know. Okay, so that is really how you solve all of these problems. Now, one thing that you're going to be facing with is finding the efficiency, and the efficiency is actually W net over the Q hot. Okay, if you want to, it's the Q in or the Q hot, doesn't matter which, minus the Q out or the Q cold. and put them in absolute values. That way, it doesn't matter which convention you're going to be using. You're going to be always having the same value in it, divided, of course, by QH. Okay, Q hot. One thing you always, so all of these engines, none of them is actually a Carnot engine. So their efficiency is going to be less than the Carnot efficiency, which is going to be the highest efficiency, which is going to be 1 minus TC over TH. Remember, the temperature is always a positive number because it's in Kelvin. All of these temperatures are in Kelvin. Okay. So if you're asked to compare it to a Carnot engine, you really have to find where TC is and what TH is. If I go back to this example, let me see if I can pick up another pen in here in a different color. And let's say, for example, I find this temperature, I find this temperature. This one is irrelevant because it's clearly middle of some temperatures, and this temperature and this temperature. I need to ask which one is the highest temperature. It could very well be this temperature. So this is TH. I ask what is the lowest temperature. It could very well be this one or that one. It doesn't matter which one, but one of them is definitely lower than the other. So let's say, for example, this is TC. Had this been a Carnot engine, and it is not, or a Carnot cycle, and it is not, then in this case, the efficiency is going to be this much, 1 minus TC over TH. But the actual efficiency is this one. So when you compare the two, this efficiency need to be higher than this one. All the time, these questions arise in all kinds of exams. So you'll have a bunch of engines, and you really have to make decisions on them, and you have to work the algebra for them. And the algebra is usually finding the work, finding the heat, finding the energy, and then there is the other guy. Don't forget about the entropy, okay? Delta S, which is the change from of dq over t. And dq depends on the process, okay? Well, I can find what dq is in here. Or I can find the integral in here. So this is going to be just NCP, the ln of the final over the initial. This is going to be NCV times the ln of the initial, because in this case, dq is simply equal to NCP dt. And when I divide by dt to find the entropy, then I calculate it from the final to the initial, then I have that. Same thing in here, it's going to be NCV dt, that is dq. So I can find it. Here is a kicker also again. What is the entropy going in this, from this point to that point? Because this is not really a standard process. There is no formula for it. You really have to do some work to find it. So you need to find delta S, the entropy there. Since the entropy is a state variable, then we know delta S also is 0 for the entire cycle. Delta S is equal to 0 for the cycle. All state variables, their deltas are 0 for the entire cycle. So it doesn't matter where you start from, you're going to find, if you start from here, you're going to find up to here and up to here and back to here, you know what the delta S is going to be. It's going to be 0. Well, if the delta S is 0, and you know delta S in here, which is just the ln of the final temperature over the initial temperature times NCP, and this is going to be NCV times the ln of the final temperature over the initial temperature. So you know delta S in here, and you know delta S in here, and the overall delta S is 0. So you still can find also delta S for this point in here, just by adding all of these numbers plus this one and make sure it adds up to 0. So there is always a way of finding things, even though probably they are not given straight out. Okay, you can always do that. Okay, so there is always a way of finding it. Here is the thing for the exams, and I really accept it. You have to you can actually, if the area is not a common triangle or a rectangle or a common shape, that you can find the expression for it. And if the function is not given to you, then just approximate it to see how many divisions in it and get an approximate value, because that's what engineers do actually. Okay, so sometimes they get the approximate value just by counting how many squares in here, and that's what the computer does for you too. So if you give it a complicated path that the process goes through, and that path is not anywhere known, and the function is not given, the computer just calculates the area approximately, that's all, and with the precision that you want. Okay, so this is stuff that is important. So what else also in the exams, things that you really need to prepare for? I just mentioned the entropy. One of the processes that I mentioned examples for is the ones at constant pressure or constant volume, or even for the calorimetry. Okay. Okay. In calorimetry, basically what you do, you have a material with a given specific heat C, and it has a specific mass M, and you take it from an initial temperature to another temperature T2. Okay. Usually this heat, if the initial temperature is higher than the final temperature, it's cooling down. And if the final temperature is lower, I mean, it's the initial temperature is lower than the final, it's heating up. That's all. Okay. So the entropy in this case is going to be, I'm sorry, delta S, the change in the cycle, is going to be MC times the ln of the final temperature over the initial temperature. So the entropy can be positive or negative depending on this ratio. If it is more than 1, remember the T's are in Kelvin always. This is a common mistake. I know even at this level, I see people who forget to make the conversion. Okay, if the temperature is given in degrees Celsius, convert them to Kelvin. Okay, and so I'm going to find the entropy in here. If I'd say, for example, I have a cup of coffee. Okay, warm. Its temperature is given T1, and I put it in the environment. I think I did this example in class. Okay, and it's room temperature. And you ask the entropy in here, it's fine, you can find it. If I tell you what the coffee is made up of and how much it is. So if I know what C is and what the mass is, then we can find the change in the entropy. The question is, how much the change in the entropy for the rest of the universe? It's not this value, by the way. But we need to be able to find it. If this is a heat sink, meaning its temperature doesn't change. So its initial temperature is the same as its final temperature. It never changes. So if I am tempted to put the ln in here and put T over T, the ln of 1 is 0 no matter which base you're putting it in. So it's not going to work. And that is not true, by the way, because that formula works only for this type of process, because it's still delta S is really the integral of dq over T. And the only reason why I found this one is because MC times delta dt is the dq. In here, the Q, the temperature doesn't change. So it's going to come out of the integral for the heat sink, and it will be left with just Q over T. Now, how much Q there is? Well, it's the Q that was, in this case, drained from the coffee to cool it down. And the Q in there, for this particular example, is equal to MC times delta T. So I plug in this number divided by T, and now all of a sudden, what this T is actually this difference between these two temperatures, the final minus initial, and that's going to be the Q that was drained in here. If it is really heating up, if it's cooling down, it's going to be, again, dumped to it, okay? So this is something that you really need to pay attention to sometimes, and I know under the stress of exam, people immediately think that this is some sort of a general formula. It's not. And they plug it even for a heat sink, like the room, for example, and then we'll find 0. That's not true, okay? At the end, always keep in mind the entropy of the universe. If you're asked to add up the entropies to check if this is true, this must be always true. This is the second law of thermodynamics. So if the first one was, I don't know, 2 joules per Kelvin, and the second one, let's say, for example, 1.93 joules per Kelvin, and this one actually is clearly negative. So if I add the 2, it's going to be 0.07 joules per Kelvin. So the entropy of the universe must have increased by this amount. So it's always going to be increasing in a realistic scenario, okay? So this is basically some of the things that you need to remember. The other thing is calorimetry. I just mentioned it. Basically, when you have a substance in here sitting at a given temperature and another substance sitting at a given temperature, the cup of coffee in the room, and this is the initial temperature T1, this is an initial temperature T2, and both of them, they will reach a final temperature. So in this case, the first Q, let's call this one M1, has specific heat C1, and this is M2, has specific heat C2. So the energy lost to one is the energy gained by the other. The heat lost by one is the heat gained by the other. And that's how I find the final temperature. I know this is the easy question, and a lot of you did it probably in chemistry and stuff like that one. But remember, this is actually was one of the labs. Okay. Now, in terms of the last thing that you really need to remember and prepare yourself for is the conductivity. Okay. That too requires some calculations, sometimes integrations and things. I did include a lot of problems that we solved them. They're actually in all the weeks that we did in here. The exam is going to cover chapters 17, 18, 19, and 20 only. So chapter 37 is not included in the exam. The lab for chapter 37 has been postponed, okay? This lab is actually preparation. A lot of the labs we do and a lot of the problems I did solve for you guys are actually helping you to prepare. I really want you guys to go through the preparation and prepare for it well. And if you have any questions, please shoot them, send them. Sounds good?
Yeah.
Okay, very good. Thank you, Alexis. Okay, everybody, thank you very much. I'm going to stop recording. I think we still have a few minutes, actually. Yeah, because we started the class before we recorded. We were talking about specific issues related to the lab, and then Alexis was kind enough to share her screen for you guys. So hopefully you guys will benefit. And if you have any questions, please let me know.